Okay, today we want to further design this structure. But before we proceed with this protastructure design of this very structure that we have at hand, we want to design the cantilever of this building. Now, what we are basically doing in this design is we want to compare the design of protastructure with our manual design. In other words, we want to run the software design and also design this very project using the manual calculation. Though it might not be completely manual calculation, but something that is about 70 to 80% manual calculation. So that we can compare and contrast the result of the protastructure and that of the manual calculation and see the one that is more effective and more economical. So before we further finish up the design with protastructure, let's just design the cantilever today. So we have this one is not a cantilever because it's being supported here and also being supported here. But this one is a cantilever because there is no support at the edge. It is free. It is free. So a cantilever is actually a structural element that is fixed at one end and free at the other end. So we are going to design this and check if the length of this cantilever and this one are the same. So let's look at this one also so that we know. Okay, so this one is actually 9987, so which is more critical than. So let's check this one. Let's check this. Okay, so this one is 73, so we can. Okay, then we now design this. So we are going to design 3 cantilever. So we are going to design this. We are going to design this. We design this. Okay, we design this because this is. Let me confirm this dimension again. Let me confirm this dimension from here to here. Okay, so we assume that this dimension and this dimension, they are the same. So we can pick one. So I want to pick this because of this adjacent span of that cantilever, which is 3, which is more critical than this other one. Okay, so we are going to design this cantilever, design this, and then design this. Okay, so let's go. Okay, so we open our design template. So we can call this one cantilever slab design type 1. So type 1, so let's choose our type 1. So let's call this one type 1. Let's call this one type 1. So we call this one type 1. So the cantilever length here is 712, which is the same thing as 0.712. Okay, so the critical partition span adjacent to cantilever. So we look at this. So this is that critical span, which is 3450. So this becomes 3.450. Okay, numbers of story, we have just one story. Then height of wall for each floor, height of wall for each floor. So we go back to the drawing again. Go back to the drawing. Now this is the cantilever. This is the cantilever. So the height of this wall is going to be considered from here up to this level, from here up to the roof beam level. So we assume this to be 3 meters. We assume it to be 3 meters. We assume that to be 3 meters. So though we might not be able to get, there's no section. I think this it is from section that we really know the. It's from the section that we really know the real height. So we are going to assume this. We are going to assume this to be 3 meters, not up to this 3 point something, because this might not be the accurate height of this. So this is 3 meters. So we come here, we put 3 meters. Now height of wall for each floor. Height of story is 1. Height of wall for each floor is 3. Overall height of wall considered for cantilever design is 3. Yes. Slab thickness, we are using 150. Concrete cover to reinforcement is 25. Then assume main reinforcement. So we are going to assume 12 here. Then characteristic strength of concrete, cylinder strength 20. Cylinder strength is 20. Then for that of keep strength is this one. Then characteristic strength of steel, we have this. Then density of concrete. Now, since in the software we were using 24, so let's also use 24 so that everything will correspond. Then roof loading, live and dead, we have 1 point. Then imposed load, our imposed load here is 2.0. Remember, we use 2.0. Then design working life of structure is 50. Then intended use of structure, we have already defined it. Residential, fire resistant is 1 hour. So unit weight of block, 2 to 5 blocks is 2.8. Then effective depth of cantilever will now be 150 minus 25 minus half of the main diameter. So this now become 1192. 1192. Okay. Okay, so let's look at the loading on the cantilever. Let's look at the loading on the cantilever. The first thing is that the cantilever will have save weight. So save weight of the slab. Save weight. This is a save weight of this slab from here to here. So this slab has a save weight. So we consider that save weight. We consider that save weight. Then the next thing is screeding. Screeding. So we assume screeding of 0.5. So when you look at this drawing again, you see that there will be a screeding on top of this slab. So there will be screeding. So you have to also add up that screeding, the weight of that screeding the the cantilever. Then we have finishes, rendering, and services. We know where we got this one. Then partition 1.1.0. Then we have total dead load, which is equal to this. Total dead load is now a combination of some summation of everything. Then we have the live load. Okay, so load combination and arrangement. So we have these. So these are load. This is the UDL that is acting on the wall. The UDL that is acting on the wall. So this is the UDL that is acting on that wall. Okay. Okay. So now we calculate the point load. So what constitute point load? Number one, the wall load and finishes, which is this one. Wall load and finishes, which is this one. Now remember that this is a point load. So that is why we just multiply it by the factor of safety for the dead load. So that is, so That's why we have this one to be 14.1. And remember that the other wall load we don't multiply. Instead, it is when we take it to the software that the software during the design load combination, the software will now handle everything. So here, since we are now generating this as a point load directly on this. Okay, so let's go back to the drawing. How do we look at this? This is where we have the point load. So this is the point load. This is the point load on this cantilever. So this is the point load on the cantilever, and it comprises of the 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 weight of the block, the weight of this block, you multiply by the height of it, then finishes and every other thing that constitute that point load. Then we also have the roof load. The roof load also still constitute a load on this cantilever. So that is why we have this roof load. So the roof load will now be 1.5 by 1.5 times the adjacent critical span, which is 3.45. Then you divide it by 2, and then you add these. So at the end of the day, we have our point load to be 17.9. Then the uniform distributed load here to be 10.7. So this very load that is acting at this point is 17.9. This is 17.9. From here to here is 17.9. Then the uniform distributed load is about 10 point something that we have. So, okay, so we calculate the moment, we calculate the moment for this. So the moment will now be WL squared plus BL. So now there is something I want to do for us to check if our calculation is correct or not. Now there is a software I want to use right now to I want to use that software right now to calculate this again so that we can compare our moment if it is correct or not. So let me quickly go to that software and use it immediately. Okay, so it is called Beam. So let me just quickly use this. So I will go to, I'll just click on, I will click on here, add Beam section. So this will be, no, let me set the unit first. Units. So we are using meter. Okay, so the next one is we want to define 0.712. 0.712. Okay, so now we um, add our this thing. So it's going to be fixed. So fixed at one end, then free at the other end. So let's define our load. The first load I want to define is going to be a uniform distributed load. So the location of this load is going to be, this is from zero, then load at 0 will be minus 10. Let me check out. Okay, 10.7. 10.7. Then we also have 10.7 here. So we click on OK. We click on OK. Then we go back to load again. Go back to load again. So this one will be concentrated load. So what will be the distance? This will be 17.9. 17.9. Yes, 17.9. 17.9. So where will it act? It's going to act at 0.712. 0.712. Okay. So I want you to check something. I want you to check something. Now, when you look at this, when you look at this moment at this moment is 15.5. 15.5. This moment is 15.5. Now let's look at our own calculation. You see that this moment is also 15.5. So meaning that using this beam marks and using our manual calculation, we have the same result. So I just wanted to do that for you to see. Wanted to do that for you to see. So this is 15.5. This is 15.5. So this is a shear force. This is shear force diagram, and this is how the bending moment look like. Okay, so let's proceed. Let's proceed. Okay, so now that we have gotten our moment, so we calculate reinforcement at support. Reinforcement at support. So this is the formula for it. This is the formula for it. So K is equal to MBD squared FCK. Now, the B here is 1000. Remember that we designed a slab per 1000. We designed slab per 1000. So B here per 1000 width. Per 1000 width. So that is the, the area in which we design our slab. So we now have this to be 0.055, which is less than 0.167. So we calculate for lever arm. So our lever arm is equal to this. So we adopt this. Now, this formula says that if this is less than this, then we adopt this one. But if this is not less than this, then we will adopt 0.95. So when you check, you discover that this one is the same as this. So that's why we adopt 0.95. So we calculate Z. So Z is equal to 113. Then we calculate the area of reinforcement required. So when you look at this area of reinforcement, we just have 384. 384. Then let's see what we provide. We provide, we say adopt reinforcement spacing of 200. So when you do that, you have 566, which is greater than this one. So which means that area of reinforcement provided is adequate. Reinforcement, okay. So distribution reinforcement, secondary reinforcement. We said that it is 20% area of reinforcement provided. So when you look at this, so we can say that we provide H10 at H10 at 250. So which give us 3114, which is okay. So we check for deflection, just a process of our design. So we know that deflection is already okay. Require percentage of compression reinforcement. So the concrete is highly stressed because we have 0.0, which is 0.332%. So we check for span to effective depth ratio. Okay, let me explain why we say that the concrete is highly stressed. Now, this table 7.4 says that if this area of compression, because why we say that we are using it is area of compression is that there is we are designing for that it is the reinforcement is placed at the top, not at the bottom. So if it is at the bottom, it would have been area of tension, but here it is at the top, so it's area of compression. So here you see that if rho is equal to 0.5, if this is equal to 0.5, then concrete is lightly stressed. But if this is equal to 1.5, then the concrete is highly stressed. So in this case, what we have is just 0.32. So the concrete is lightly stressed. The concrete is lightly stressed. So we calculate span to effective depth ratio. span to effective depth ratio. So let's look at the span effective depth ratio here. Now we are designing a cantilever. So the so the span effective depth ratio is going to be 8. Is going to be 8 because the concrete is lightly stressed. The concrete is not highly stressed. So this span effective depth ratio is going to be 8. So the factor for that is going to be 8. So here will be 8. That will be 8. Okay. So we calculate for deflection. Now the value in table 7.4 is based on the assumption that the steel A stress at critical section under the appropriate design load is at serviceability limit state. So this is the stress for it, the steel stress. Now, since we are not using 500, remember 500 Newton per millimeter squared as the steel stress for our design, we are using 410. So since we are not using 500, we are using 410. So we have to modify this formula. We have to modify it. So since we adopt a steel stress of 410, the value in 7.7.4, 7.7.4, yes, 7.4 table can be multiplied by this. So this now become this the steel stress that we are using than the area of reinforcement required all over 500, which is the steel stress of 500. So when you are using Euro code, it is expected that your steel stress should not be less than 500. But in a situation where it is less than 500, you have to modify the stress. They have to calculate the steel stress. So this will now be the actual steel stress that we are going to use for this. So at the end of the day, we now have the steel stress to be what? 174.1. So we now modification factor now become 1.77. Then therefore, modified limit span effective depth ratio is equal to this 8 times this one, so which give us 14.25. So the actual span depth ratio now become this divided by this, which give us 6 shorter span and depth for check. So actual depth ratio is equal to, so which is okay. So what we have done is okay. So at the end of the day, what we have is that the top reinforcement will now become H12 at 200, then the distribution will become H10 at 250. So we are done with that very slab, which is type 1. So we are done with type 1. So let's quickly go to type 2. Let's quickly go to type 2. So we assume that this one is type 2. So let's check the dimension again. So the dimension is 987, 987, 987. So that we will not really waste time. So what we do here is that we just rename this cans 2 design, can 2 design. So we come here, click here, just copy. Then we paste. So here we quickly change this to type 2. So we come here, change this quickly to 987. Let's confirm again. 987. Let's confirm the 987. That is fine. 987. So we also look at the same also because we have already explained this. So what we will consider right now would be if we change the length using this one, you will see also that our moment will also be the same as this. So since we have already confirmed the first one, there is no point for us to go back because of time. Okay. So at the end of the day, let's check out our reinforcement. Let's check out our reinforcement. Okay. So meaning, look at what happened here. Because the cantilever span has increased. So the reinforcement fell because H12 at 200 is not available. So you come here, we can adjust this. I can say 175. So when you check, make it at 175, you see that it is okay. It is so every other thing are okay. Every other thing are okay. Okay. So I think that's all. Then we move again to the last one. We move again to the last one. So we can call this one design can 3. So we copy, come to this one, we paste. Okay, so we change this to 3, change this to 3. Okay, so let's look at this other cantilever. Remember that in the software we have extended this. So let's also extend this. So let's just have just here as the cantilever. Let's just have just here as the cantilever. So um, let's get the measurement. So from here, okay, so this is 1.838, 1.838, 1.838. So this will now be 1.838, 1.838. Okay, so we go back. Let's check the architectural drawing. Now, when you look at this architectural drawing, you see that there is no wall load here. So meaning that this cantilever is just it's just like it's just a balcony. There is no wall load here. There could be some. There could be. Okay, let me look at. Look at. This is like a railings. So this is like railings. Look at it here. Look at the cantilever here. So there is nothing like wall. There's nothing like wall. So in this case, there's nothing like wall. So in this case, what we do is that we will remove wall load from it. We remove wall load from it. And now put another thing, which is like rails. This is just like rails. Maybe or burglary, something that connects the roof load to it. Now you see that the roof load will still be applicable, but because there is something like a protector here that links that is connected to this cantilever. So we need to put that into consideration when we are doing our design. So here the oh sorry in cant 2 we did not we forget to look at the adjacent critical distance. So here let's look at this. So we have 373, 3736, 3736. So for this one, we have 3736. Okay, 3736. I think it won't change anything. Everything will still be okay. So let's look at the reinforcement again. So as you can see that the reinforcement the area of reinforcement required has increased. Initially it was 585, but it has increased to 595. So you know that has a significant impact on the cantilever. So this one, let's look at that span. Let's look at it. Okay, so we pick from here to here. So we have 1838, so which is it's also 1838. So here 838. Okay, so everything remained the same. Everything remained the same. Now everything remained the same. Then, but when we come to this point, where is it? Let's get that. Okay. So when we come to where we have the point load, so this will go because we don't have this wall load on it. We don't have the wall load on it. So let me check where I will remove that. Okay. So this has gone. We don't have the wall load on it. Instead, we can say something here. We can we can say something here like weight of fixed protector or steel protector, steel burglary, burglar, burglar. I don't know if I'm correct with the spelling. Burglar. Okay, however it is. So we can assume this to be 1.0. Assume this to be 1.0. Assume this to be 1.0. So this will no longer be wall load finishes. Or we can say this is rail. Let's call it rail. Let's call it railings. We call this one railings. We call this one railings. So this formula would not be applicable here. Instead, so we can assume this railing to be, we can assume this railing here to be 1.0. So we just put the 1.0. So let's call this one rails, railings. Okay, weight of railing. Then the roof load is still okay. So this is just the point load that we have, which is not very significant. It doesn't have much impact. We look at the the moment that we have here. So we have 23.7, 23.7. So let's look at the reinforcement, how it had the impact on the reinforcement. So the reinforcement here is the area of reinforcement required is 607. So because of this, we can increase this to 150. We can reduce the spacing to 150 because of other unforeseen uh, factors. Okay, so this will be Y12 at 150, Y12 at 150, Y12 at 150. Then the distribution, like the secondary reinforcement, H10 at 250, it is okay. Then every other thing. Okay, let's check this. Okay, we check this. This is 0.5, which still fall within the lightly stress, or 0.51, which still fall within the lightly stress concrete. So sorry, this is 8. This is 8. This is 8. So our deflection is still okay. Deflection is still okay because the actual effective depth is equal to 119. Okay, so that is basically how you can design your cantilever and check the deflection and every other thing that you need to check. So in our next model, we will now um, in our next model, what we will do will be for us to what we will do will be for us to edit the axis, that is the grid line. So we are going to edit these grid lines using the AutoCAD. So we are going to edit the now the reason why we will edit these grid lines to correspond with what we have in the AutoCAD is so that when we eventually export this model to AutoCAD, the beam grid line will correspond with what we have in the AutoCAD. So thank you very much. And I believe that you have learned something. So at the end of this very series, you will be able to judge if using Protas software is economical compared to, apart from the fact that it saves time compared to the manual calculation, we have to we will have a very sound knowledge to be able to judge any software that we use and know if the software has over designed or not. So thank you very much for being in this journey with me together. And I believe that you have learned something today. So see you in our next model. Bye.